Right, so let's get started. So the Zoom people, let me know if they can't hear me. All right, um, so it feels like years ago when we last had this lecture. All right, so we had let's just briefly summarize where we are. So we spent quite a bit of time talking about Christodoulou's work concerning self-similar solutions to the Einstein scalar field system. We saw what so-called scale invariant solutions. We saw which ended up not corresponding to naked singularities, and then we saw these twisted ones, which we argued corresponded to naked singularity solutions. Um, okay, and then all right, I talked about briefly, there are lots of interesting questions still in spherical symmetry for even for the scalar field model. But then I said the rest of the course, we're going to try to look at, in the time we have remaining, I'm sure we will run out of time before we do all the things that I want to do. But in the time that we have, I want to discuss trying to understand some aspects of those, if you can find similar phenomena in the Einstein vacuum equations without imposing spherical symmetry. All right, and before we can jump into that, we have to introduce sort of unfortunately some sort of technical baggage. Just basically, if you're not working in spherical symmetry, life is harder, of course. And that's what I had started last time. So talking about, and in the particular tool that we were going to use is the so-called is the double null gauge. So because I don't, I'll quickly recap what we had said about that, since presumably people have, well, I don't, yeah, presumably people have forgotten exactly what I said. Okay, so first of all, so remember that so way at the even I guess maybe during the winter school we talked about how every Lorentzian manifold can be locally equipped, right, with this coordinate system like this. These boards are small. Oh my God. Can be locally equipped with um coordinate system where the metric takes the following form. Right. And remember, so U and V, U and V are some functions. Level sets of U and V are null hypersurfaces. And this theta A, these are coordinates, right, on these, what we call on each SUV. So SUV stands for the topological sphere lying at the intersection of a particular constant U and constant hypersurface. All right, then in this the double null gauge formalism, what you do is you decompose all tensorial quantities on the spacetime are basically you decompose you project everything onto sort of the spheres, and so you write everything as either scale, as some any spacetime tensor you can write by expanding in a suitable sort of null frame. You can write as a collection of objects which are tensorial on each of the spheres, right? And so we had this, the null frame that we would use is this one. All right, and so you can check that, right? G of E4, E3 will be -2, and then so these are these two null vectors. In general, on the sphere, part of the philosophy of the double null gauge is you try to work. It doesn't, you don't necessarily, sometimes you have to sort of pick gauges on the spheres depending on what you're doing, but you try to often do computations geometrically with respect to the sphere. So here we're making very explicit choices, even though part of the reason it's kind of, well, I mean, the ambiguity of the choice of these is not very big actually, because it's just the null directions are pretty rigid once you fix a sphere. You can rescale these, but you can kind of understand that. But anyway, so sometimes so you might just so often we'll just write, EA will just stand for some, of course, locally defined frame on a given SU. Right. Okay. So, right, and then I introduced this convention already. So, so Latin indices, um, A, B, whatever, these are always running between, you should think they're running between 1 and 2 and correspond to tensorial objects on the sphere. The Greek indices, alpha, beta, whatever, run from, depending, maybe say 0 to 3, correspond to space-time tensors. Okay, so that's sort of what I said last time. And then, all right, so then you start decomposing everything. Well, first of all, hopefully, that's just a quick review. Yeah. Zoom. Okay. All right. So then we have this hierarchy of these unknowns. Oh yeah, but then there was this definition, right? Sorry, of an SUV. Again, let me just try to do it quickly without spending too much time. So, because I said this already, but the objects we work with, we'll call them SUV tensors. So these you would write like, so of course, one possibility is a scalar function, but in general, it's just going to be a tensor on the space-time, which vanishes whenever you plug in, so we'll think of it as something that eats vectors. So I put the indices downstairs. Of course, you can raise and lower indices with the spherical metric, but we think so. This is just going to be a space-time tensor, which vanishes when you contract it with something normal to the spheres, right? So we talked about that already. And then we talked about how you have, actually, I don't remember if we talked about it, but you can define, there's then, all right, so in general, right, the geometric way to differentiate, it would be using the Levi-Civita connection. But we can now, so given an SUV tensor, we can define, we'll define two operations. So we'll have this novel of 4 of this is by definition, all right, so I'll say what this is in a second. So you're going to take the covariant derivative. So every SUV tensor can be considered, trivially is also a space-time tensor. It just vanishes in the normal components. So you can take its covariant derivative of the metric. So D is the covariant derivative of the full metric. So I can take this full covariant derivative. But then given any space-time tensor, I have this thing. So this board is so small. So I have pi from like space-time tensors to SUV tensors, which all it does is it just deletes, it just basically when I uh this tries to eat some tensors, the first thing I do is I delete anything normal, to it. So it automatically you just force it to be an SUV tensor, right? And so this gives us right, and then this thing's an SUV tensor. Anyway, so this gives us a notion of this is the replacement for doing sort of covariant derivative in the E4 direction to an SUV tensor, right? Then you have there's a similar thing for oh, I guess and the 4 here corresponds, of course, to doing E4, right? I mean, you do the usual abusive notation, but you just write 4, not E4. Okay, then there's similar things. All right, and then this, whatever. I Okay, so that's that. We of course, if we want to take derivatives along the sphere, there we can just use sort of this, remember G slash here is the induced metric on the sphere. Remember there's this thing, this is the induced metric on our SUVs. And there's a general notation is that we use a slash. The slash denotes anything which is sort of geometrically defined by the induced metric on the sphere. So in particular, we can also take this is just, this for fixed UV, an SUV tensor is just a tensor on the sphere. And so I could just take the covariant derivative using G slash. That's just the usual definition. Okay, so that's that. Formalism, any questions about that? Yeah, okay. All right. Okay, so now we have this I guess also uh sorry?
I think the highest projection of this space from.
Yeah, it's just a natural like if you just um I mean it's just this, you have yeah, of course SUV tensors are I mean they're still defined on the right. An SUV tensor is for every so for every U and V you get a tensor on the sphere. So it's still sort of it has UV dependence.
Okay.
Just for every fixed U and V, it's something you have something tensorial on the sphere. Like this whole decomposition for a scalar is something really silly, right? So for a scalar, it's just saying you have like h of u v theta a. That's a scalar function on spacetime. That's also a SUV scalar because for each u and v, it's a function on the sphere. The so this doesn't mean this is only well, I'm saying here there's nothing to do. It doesn't because it doesn't act on anything.
No,
So
just said here, I guess for maybe my understanding initially that I didn't understand that what we mean by SUV, that's it's not like something that is intrinsic to
for each u and v, it's a tensor on the sphere. Yeah.
oh, okay.
Yes. No, I think yeah.
Yeah.
Yeah. I just wanted to emphasize that it's not really that it's a two-dimensional object, right? Because it depends on u and v.
Yeah.
For each UV, it's just like a way to organize the tensor calculus. I mean, they're all yeah. It's a way to organize the tensor calculus, which like emphasizes like the importance of these particular null directions. And like the things on the sphere is kind of saying, well, that's like, sort of less secondary. So you treat that just geometrically. And what we want to really focus on like, gauge choices are with these null directions, you know. Other questions? Yep. Okay. So, all right. So now let's go through the sort of different levels of unknown, different levels of unknowns. Do I dare to do this? Let's see. I mean, certainly the first one makes sense. It makes sense to move this board and right here. Oh, I guess I see it. So you're right here. And then on the next stage, I erase this. That's what makes sense.
And then you right there and then you move back and you erase.
Yeah. Okay. Wow. We figured it out. Okay. Cool. All right. So there's sort of these three levels of unknowns. Okay. So you can think that there's sort of three levels of unknowns. All right. The first one is kind of just these are the metric components. All right. That's, nothing. Okay. Maybe I can introduce so these pieces on the sphere. All right. Nothing there. All right. And then the next level of unknowns is, what in this in sort of mathematical relativity land we call Ricci coefficients. These are just going to be various Christoffel symbols, but not sort of all of the Christoffel symbols. Maybe I can yeah. So the point, so it's not, why is it not all the Christoffel symbols? This is related to how that where you try to work geometrically on the spheres. So because we're not going to, at least on the first pass, this gauge is agnostic about whatever you're doing on the spheres per se. We're going to, we're not going to introduce, for example, the just the spherical Christoffel symbols, like you won't see like of this induced metric on the sphere. And here we're not going to put these Christoffel symbols because we're not going to ever estimate those, because you can think it doesn't make, because if we're trying to be agnostic about picking a system on the sphere, then it doesn't make sense to estimate their Christoffel symbols on the sphere, right? Because they could always be 0 or whatever, right? But basically all the other ones okay, I'm being very sort of rough here, but we can be more explicit. So let me write them down. We're going to quickly get very tired of formulas in this gauge, but it's good to start with something. All right. So what are these? So these are some like a subset of the Chris alpha symbols. All right. So the first one is so and on all of these, often they have there's this what we call like conjugation. There's this notion of conjugation where you define some quantity, you can switch the role of the 4 and the 3 vector, and sort of everything uh is basically symmetric with E4. We saw that when we were doing the things with Christodoulou solutions. I sometimes would write something just for in the V direction, and then I said you can do it on the U in the same. So there's the same structure here. So sometimes you could write half as many things and just say the same, Okay, so the first unknown, so we have here, so chi AB, this is well, okay, so here's the definition. So you can think that these are all these are quantities which allow you to which are what you need if you want to relate you can write like about formulas which just relate various covariant derivatives. It's based on covariant derivatives to sort of SUV derivatives. SUV derivatives being the nabla 4, nabla 3, or the geometric derivatives on the sphere. And okay, I mean, uh, you know, you can obviously compute such formulas using this, and in various Christoffel symbols will show up, and these are included in these Ricci coefficients. So one of the ones that shows up, so and the way I'm writing it makes manifest their use in such a formula. So for example, you could start with, you might want to know, right? We have all these vectors. So you have E4, you might take the covariant derivative with respect to A of E4, all right? And then, for example, um, you want to know how it looks back on the sphere, then we call that chi AB. This is, of course, also just the second fundamental form. This is the second fundamental form, right, of SUV with respect to E4, right? So we have a hypersurface, so we have the normal space is two-dimensional, so we have E4 and E3 span the normal space of the sphere, associate to each. I mean, usually second fundamental form is the thing that bundles all of those together, but you can also think that there are two second fundamental forms, right? Each side. All right, so you have that. And then you also have, right, like I said, there's is just conjugated. Right, so pi bar is if you switch the 4 to the 3. Right, those are some important ones. These are maybe well, I don't know if it's fair to say that one Ricci coefficient is the most important, but in some sense, these are like if you had to pick one, that would kind of the most important. All right, so then there's this one called eta A. I guess I mean one way that these are sort of you can think these ones will roughly correspond to in the scalar field system. Sort of correspond to derivatives of the the one with E4 sort of corresponds to the dV of the scalar field, and this one sort of corresponds to du of the scalar field. That turns out to be a useful paradigm. All right, so then there's one that doesn't really have any analog in spherical symmetry. This is eta, so this is minus 1/2 g. No, this is just the general metric, right? Yeah. This is D3 of, yeah, because in spherical symmetry, remember I wrote out the equations. There's just no comparison in the level of complexity. I mean, there's just like 4 equations, or there were 6 equations maybe. All right, so you have this. Okay, and then there's equals some other stuff. And then, okay, now I'll erase this. Yeah. All right, and then well, okay, let me just write this out. All right, then there's little omega, or many of these numerical factors are just various normalizations that, somebody found useful somewhere. It's not particularly important. they're not particularly meaningful. Of course, it's important. I mean, once you pick a normalization, you have to stick with it. All right, so those are related to decomposing, doing the 4 one with the 3 and then decomposing it back on the 4. And then finally, there's the last Christoffel symbols. But I mean, the last Ricci coefficient. Like I said, this is not all of the Christoffel symbols. A. All right. This one is sometimes called torsion. We'll see that it's very related to these ones. Okay, so now, so this is written in the form, like I said, these formulas are in the form that you would use if you wanted to decompose the space-time covariant derivative of various parts of the, so remember, you should think we have, I mean, if you wanted to, so you have these E4, E3s, and if you wanted to take, various covariant derivatives of them and then rewrite them in terms of, the, things on the sphere or just decompose it in terms of the SUV formulism, these quantities show up naturally. That's written like this. But there's also, you can also, but if you want to think about like maybe from a point of view of proving estimates for the metric or something, and this isn't quite, you want to see somewhat more like explicitly an equation. So of course, Christoffel symbols should be derivatives of the metric, right? So you can also, and you can just work out from these formulas. And this is perhaps a little more intuitive. So first of all, just some other notation. So the second fundamental forms, we decompose into 2 pieces, trace-free part and a trace part. So this is trace-free with respect to the All right, so that decomposition, part of why that's very useful decomposition is later we'll see that the trace of the second fundamental form, again, if you studied singularity and completeness theorems and relativity before, you know that the traces of the second fundamental, this is the thing which shows up is driven by Ricci-Durry. So it's sort of like somehow this one is less free than this one. I mean, somehow the shear contains kind of a lot of the information because I mean, once you know this and I mean, of course, there are other unknowns in there. In reality, the story is actually more complicated, but some schematic level, once you know this, somehow trace chi just comes along from the ride because you will solve Ricci-Durry, and I'll write that equation. But all right, yeah, okay. There's that again. You do the same decomposition. Blah 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 blah. Okay, so what about these other ones? Let's maybe start with this one. So these ones turn out again. You could just if you just play around with these formulas, do the usual thing, like, use compatibility of the covariant derivative with the metric. So this is equal to, E4 applied to G of E3, E4 minus the other one, you do all those things you do when you learn Riemannian geometry. They work the same here. What you can show is that omega is equal to minus 1/2 of nabla 4 of log of capital omega. Right. Again, this is the notation for the SUV covariant derivative, but of course, this is a scalar function. So this, just making sure there's a lot of notation. This is, of course, the same as just saying that frame, right? Because it's right. So what you see is, okay, so this is a particular derivative of that. All right, then, okay, and then omega bar is just the other derivative of the null lapse. All right, and then so where is this guy? This torsion relates to a particular derivative of B. So this B, remember this B, this is this term which prevents the metric from being like diagonal. You had the sphere, the G slash part, you have the null lapse part, and then there's a thing which mixes the U and the theta. That's this thing which we call the shift vector. So so this is, of course, so this is a vector field. So if I take the derivative with respect to d by dv of that, that is equal to minus 4 the null lap squared times zeta. Right. Again, you shouldn't think that these are maybe tedious to find, but are not. This is not, you shouldn't think this is hard to get from here. It's just planar algebra. All right. Indices. So indices of an SUV tensor, right? We raise and lower with G slash, right? Because they're for each U and V, it's a tensorial object on the sphere, so we should use that induced metric on the sphere. All right, so okay, so one thing you see is if you're trying to control something about Einstein equations, once if you control omega or this, you can integrate them to try to control this. Yeah.
To respect to.
This is the lead, so this L means is lead derivative. Yeah, so L. Yeah, I mean, this is one of the things. I mean, you see that somehow when you try to do estimates at the level of directly at the metric components, it's harder to be like fully sort of the more geometric thing you might vaguely think is use covariant derivatives. But I mean, you can write something in terms of covariant derivatives, but estimating, you have a tensorial quantity as your metric component. It's tensorial on the sphere. But if I rewrite this with a covariant derivative, of course, lower order terms, that means they're lower order terms which are Christoffel symbols. Like, that lower order term is like I mean, we're estimating a metric, it's somehow like the regularity is really is weird. So somehow this is kind of the best way to write it. But does it make sense what I'm saying? Just that like it's this issue that, I mean, of course, the most geometric thing you can do is work with curvature, but then you have to take two derivatives. Right? I'm just saying there's this give and take that you get more geometric when you take more derivatives, but sometimes you don't want to take derivatives. Anyway. All right, so that's that. And then there's a final one. So then there are these eta, the eta and the eta bar. These ones, eta and eta bar, which I'm now going to hide. Anyway, at this level, when your first, introduction to this, the exact formulas are obviously not important.
Question.
Yeah.
This omega will be the same in spherical system, right?
It's the null lapse, yeah.
It is completely the same. While eta is zero.
In spherical symmetry, eta will have to be zero. Yeah, I mean, well, yes. I mean, we'll see. We haven't seen yet. I mean, so this one certainly has to be zero because in spherical symmetry, you can take this B to vanish, and so zeta would be zero in particular. We'll also see that the eta and eta bar will be zero. Yeah. So let me erase this now. Okay, and then so eta and eta bar are given by so this is equal to torsion, this torsion guy, which we know is like a v derivative of the shift vector in some sense, and then you get this an angular related to an angular derivative of a lapse, and then sort of the conjugated version is this. Right. So there's this thing here that sort of I mean, this is sort of a common thing in geometric, these really geometric PDE is that, especially if you do these kind of big frame decompositions of things, there's a lot of overdeterminedness. So for example, between the torsion, right, and eta bar and eta, between them, in terms of derivative, there's really just like there's like the angular derivative of the lapse and the v derivative of B. But then somehow they're three quantities. And they're three quantities because it's really those later, if you're writing things geometrically, it's natural for allow those three quantities to appear. But in some, you only need if you know any two of those three, you have the same, any one of them is expressible in terms of the other two, right? I mean, manifested from this. Right? But this is a very standard feature of even Riemannian geometry. When you do this like frame decomp, you see this all the time. There's a lot of overdeterminants, which can be annoying if you're trying to use that system to directly prove existence, for example, of a PD, then that's a little annoying. That's overdetermined, right? So, okay. If you already have a solution, you're just doing estimates. It's maybe less annoying. All right. So then, yeah, and then of course, yeah, I said these were the second fundamental form, but that of course means the following, right? So the chi AB is the second fundamental form of the metric. So that means that if you take the Lie derivative of G slash with respect to E4, then this is okay. So that's, I guess my one of there are so many factors of two, again, at the level we're doing things, don't worry about that. If you later work in the field, you have to worry about that. Okay, so again, note that maybe I'm making belaboring the point too much, but note sort of the only direct derivatives. So given the Ricci coefficients, the only derivatives of, for example, G slash that we can recover directly from the Ricci coefficients are E3 and E4. We don't see angular derivatives of G slash. Why? Because we're being geometric on the sphere, and first derivatives, if you don't pick coordinates or a gauge, you can't talk about first derivatives geometrically, right? The only geometric thing would be like the Gauss curvature, because G slash is two-dimensional. So the only geometric thing, the first thing that would show up would be Gauss curvature. We could do that. Well, right now, Ricci coefficients are only things at one derivative of the metric. Okay. Oh, wait. There was a question. Oh, I didn't make a thing there. Is the knobless slash the same as the ones defined by the projection? Oh, you answered. All right. Yeah, sorry for missing that question. Any questions here? No. Okay. So then, all right. So now we go to curvature. So okay. So then the next. Oh, so what's interesting is actually, so it's possible. Here's a sort of interesting fact. So you can write, and this point is not always, it's not. I haven't seen it made actually too explicitly, I think. So you can write now. So you can now write equations. So-called null structure equations. So you can write equations which relate various of the derivatives of these Ricci coefficients, basically to other derivatives of Ricci coefficients, in all sorts of ways. And it's possible just via those equations to write them in such a way that it includes the content of the Einstein equations being zero. Right. So it's kind of so that means in the double null gauge, you can write a set of equations capturing Ricci equals zero that just involves like first derivatives of the metric. Which isn't necessarily obvious because of how we did it. But what's funny is that it's like sort of no one's ever been able to use that formulation to do it. And I think, I mean, it's sort of related to the fact that it's kind of geometric on the sphere. And so you can't prove, there's no like well-posedness that can be proved there. So anything that is done, you have to always go to another derivative. And of course, the easiest way to do that is to use curvature. But sometimes it's said that you need to go to, I think people are implicitly think you need to go to curvature to see the Einstein equations, but you don't actually. I mean, I won't write them all down for you, but you can phrase everything just here. Which sort of makes sense, right? Because I mean, you should think, so maybe since I made this point, let me say 2 more seconds about it. So what I mean is that you start with something like this. You take, maybe you take like novel 4 of this. Now, so I erased it, but remember eta, or it's behind the board, but eta is equal to like, you can write it in terms of G of a covariant derivative with some random thing, right? So if I take a derivative, use compatibility, at some point in the inner product, I'll see 2 derivatives of a frame. Now I can commute those, right? Curvature comes up, and so that's what I mean. So if I take derivatives of these, I can manipulate things, and at some point, trace and use that Ricci is 0. And I can write a set of equations which, if it's true, is equivalent to Ricci being 0, right? But in practice, that's not useful for doing anything, that set of equations. All right, and what you have to do generally is you have to work, you have to go to the level of curvature. But you're going to see how immensely more complicated this is than spherical symmetry, right? I mean, spherical symmetry, you probably thought the equations were pretty gross, but I could just write them down in 5 minutes. I haven't even written down any equations. All right, so then then the next thing we do, so we have the curvature tensor, right? So this is, all right, so we have curvature tensor on the spacetime. So now I just want to follow the same philosophy. I'm going to decompose this with respect to into sort of SUV tensors, right? Just by looking at plugging in, E3s, E4s, or EAs, EBs, whatever, right? Okay, again, so it's a big mess. Again, I'm just trying to give you the flavor of the analysis here. So this first one, once you get used to the subject, all these different components start to have like personalities to you. But at first it all looks random. But so alpha AB, this is EA, E4, EB, E3. Remember the EA, EB just stand for a frame on the sphere, right? And again, this is a tensorial object, so it only depends on the pointwise value because it's curvature, right? So this makes sense. All right, that's one. So note one thing, so Ricci of G equals 0, this implies that trace of this is 0, right? Because if you trace over, well, little exercise if you will. If you trace over AB, then the claim is you'll see Ricci curvature. Okay. Okay, then you also have the bar, right? That's just, oh, this is not the correct thing. Oh, it's just my handwriting is so sloppy. So, sorry, that's important. It's not E43, it's E44. All right, then this one is EA, E3, EB, E3. That's also going to be trace free. Right, then all right, then you have beta A. This is 1/2 R of EA, E4, E3, E4. So what do we do now? I erased that. Yeah. Other questions? All right, then you have the flip, but then this one's a little sort of funny because well, this goes back to, so this particular, maybe I should just say like also 10 seconds of like history of this. So there's the idea of decomposing all of your space-time objects with respect to a null frame is something that was first introduced this first time in the physics literature, and a particularly useful way of doing that formula is something called the Newman-Penrose formalism. Now, in the Newman-Penrose formalism, was sort of more general than what I'm talking about here, and that it was you just had a frame. It wasn't your E4, E3 didn't have to come from actual like coordinate derivative, an actual foliation. In other words, there was no integrability condition on the frame, right? So that they have this general formalism. Then this sort of the particular idea of, well, do basically studying like a PDE, Einstein equations, a PDE using such a formalism, of course, then it sort of should be tied to some coordinate systems. I mean, this is initiated by Christodoulou and Kleinerman in their proof of stability of Minkowski space. And they introduced this sort of specific notations. You can think of them as specializations of the Newman-Penrose formalism. And anyway, one of the things that they did is that they made beta bar not be beta where you switch E4 and E3. And to this day, I don't know why. It's very easy to make a sign mistake. Anyway. Though again, like I said, for the level of the presentation right here, it makes no difference to you. But warning, if you ever, so I don't even know which one. So I wrote this. Yeah, I think this is sort of what's considered the definition of beta bar, but it is not the same as replacing 4s and 3s yet. Who knows why they did that? Okay, so there's that, and then there are two more. So there's rho, which is so 1/4, E4, E3, E4, E3, and then there's Then there's sigma, which is so in fourth, I'll explain what this means. Sort of Hodge star applied to R and U4. All right, so Hodge star, that's this, there are various ways to think about it. So you can think this is, well, so what is this? It's basically sort of up to, again, the exact formulas aren't important. Up to some numerical factor, it's a sort of contraction of suitable indices. It depends what kind of tensor it's acting on, of suitable indices with the volume form, which you can write as alpha beta, say gamma delta, right? And so in this case, so when the Hodge star acts on the curvature tensor, what's meant is, so the curvature tensor, you can like look in the first two slots, and you can, that's sort of because of the symmetries of the curvature tensor, that's like a two form. And you can think of the, think of Hodge star on a four-dimensional manifold, right? Maps two forms to two forms. Again, more pedant, you could think that what you do is you contract the final two indices of the volume form with the curvature, again, up to some numerical factor. You should think you do something like this. Kappa, whatever, iota. Something like this is the Hodge star. But this is just, freeze this part of the curvature tensor, consider as a two form, and map that two form to another two form. That's what. Anyway, that's just one way to think about that. Again, don't worry about. I'm just giving you the flavor of what this looks like. Right? Okay, and these are the so-called null curvature components. And sort of well, you can think these are kind of the main ones in the formalism, and then of course you should think there's also the Gauss curvature. Gauss curvature K of of each UV. Right? That's a scalar function. That's not a tensor. And these sort of contain all of the information of curvature. So in fact, you don't really need to introduce this as an unknown. So K, well, I mean, obviously there are times when K will show up naturally, but K, for example, you can find is related to so rho, like there's some combination of rho and Ricci coefficients, which will give you K. But anyway, I put it just so it's more complete. Okay, so these are the so-called null curvature components. I should say, maybe it's also worth mentioning while we're here that there's similar form. You can do a similar formalism in any dimension, but there are certain simplifications that occur in 3+1 dimensions, just relating. Well, you can think that ultimately relating to the fact that 3+1 dimensions, once we have these null, the E4, E3, and then we're left with something two-dimensional. When you have something two-dimensional, all of the curvature information is a scalar, right? That's something special about two dimensions that you just have, right? And so because of that, some of these things are like scalars so for example, there's an analog of this in higher dimensions. When you do it in general dimensions, this thing really should have two indices. It should really be like a two form, but it happens that, if you have, it's really like secretly a two form on the sphere. But of course, any two form on the sphere is basically just has to be a scalar multiple of the volume form. And so the information is just a function. So there's some simplifications, but you should think actually this would work in higher dimensions, this kind of thing. Right? Some things become tensors that are functions. And obviously this is, at some point you have to just get the curvature tensor of the whatever the thing is there. Yeah.
Would these have different definitions if SUV works homomorphic to like a different, like
no, the topology of SUV plays no role. Yeah. Okay, actually, this may be a natural time to take a break. All right, so let's reconvene at 4:05. All right, let's keep going. All right, so we have all the curvature tensors. All right, any questions in the meantime? No. Okay, so all right, so what's the what's the deal? All right, so now we're gonna like do various passes of these things in various levels of kind of of detail and engagement. So let's do the very first extremely superficial take on the structure of what are the, so this is, you can do this decomposition in any space-time. So if we impose that the Einstein equations are satisfied, what is the way that you could sort of quote unquote do estimates here? I'm being very vague on purpose to ease into the process. All right. In other words, what is the structure of the equations? All right, and I guess so. One set of these things I already said. So I already explained. I mean, there were formulas which related the metric components. Certain derivatives of the metric components were related to Ricci coefficients. So in principle, if you have some kind of estimates, if you know something about Ricci coefficients, you can use those equations to understand something about metric components. But those are sort of not the heart of the system. The heart of the system are the equations. Or the first there are two sets things. There's some equations which relate Ricci coefficients either to Ricci coefficients or to curvature, and then equations which involve sort of the highest order just curvature. But everything is coupled non-linearly. All right, so the equations for Ricci coefficients are known as the null structure equations. Null structure equations. Now, and again, being very, very rough, these are basically of the following form. So there's this kind of business, everything's so complicated that it's nice to have some schematic notation. So usually, so what we do is a little easier when you're writing in text. So lowercase c often will denote a Ricci coefficient. All right, and capital C will denote a null curvature component. Okay. And so now the null structure equations you can write them in the following form. So they're basically, yeah, well, I'll explain. So basically you will find, so either nabla 4, nabla 3, or say covariant derivative on the sphere, though again, it might not necessarily just be a covariant, there could be some, so maybe here, maybe I'll just write it like this. Some operator on the sphere. Remember, I'm being very schematic at this point. I haven't written any of them concretely. So applied to some Ricci coefficient, this will generally, on the right-hand side, you'll see different things. So one thing you'll see is, again, you can write them in many different ways. Remember, everything is so overdetermined. So there are many different ways to cast those. But one of the simplest ways to write it is you can write it so that one thing that you'll see is a null curvature component on the right-hand side. It will be linear in that, right? So, all right, and then you'll see other terms, and then you'll see other things which are, and so here I'm going to write a Ricci coefficient dot Ricci coefficient. This doesn't mean, this is not necessarily the same Ricci coefficient, right? This could be maybe different, maybe different than this, and they might be different than each other. This is just, so it's, this sort of stands for the family of the Ricci coefficient, right? But this is very schematically. So you have some differential operator on the sphere, nabla 3 or nabla 4 applied to Ricci coefficient equals something linear in the curvature tensor, and then a nonlinear term, something which is, again, in the standard way you write it, will be quadratic in the Ricci coefficients. Okay. All right, so that's that. And then okay, and so this one, so I made this point that you can, this is one way you can write it. And so how should you think? So it's possible, I mean, I'm not going to derive any of them today. Maybe if there's some demand, probably I'll just write some of the equations down. I won't actually derive them. But very schematically, how is this kind of thing, might be derived? Well, it's just so the following. So for example, you have something like, chi of I don't know, yeah, say chi of AB, right, equals G of dA E4 E3, right? Just what would the first steps be? So one of the equations, one of the null structure equations, an equation which involves novel 3 of yeah, I'd say already here there's a bit of a there's a bit of a lie. Sometimes you can also see here angular derivative of this, but okay, anyway. So one of the things that you could do is you could take level 3 of this. So this will be equal to, right, using compatibility of the metric. Well, let me say it like this. You could take D3, the space-time derivative. Yeah, sorry. You can take the covariant derivative with respect to E3 of chi, thinking of chi as a space-time tensor. From compatibility of the metric, this will be equal to G of D3 E4 EB, right, plus G of dA E4 E3 EB, right? And then here, I can switch these derivatives around and write that as I got sort of some curvature component. I didn't even tell you what my convention for the curvature tensor is. So as far as you're concerned, this is plus or minus, right? But let's say we pick it so that it's then plus, well, this thing again. All right, so I can do that. This is how I can make curvature appear. And then what I can do is I can then write this back in terms of some Ricci coefficients. So well, and yeah, if you in this case you will get yeah, anyway. Like I said, maybe I don't want to get too derailed by deriving this. But just schematically, this is how you should think you derive null structure equations. You start with the definition, which you can write in terms of, with the metric, covariant derivative, and something. You differentiate that, use compatibility of the metric. At some point you commute, then two derivatives will appear by nature of all of these. You can, and wherever you see the two derivatives, you commute, make curvature tensor come up, and then rewrite everything back in terms of some Ricci coefficients. And that's what eventually leads to things like this. Schematically. We'll see the things more concretely. Okay. So, and again, what you think, so this sort of tells, so if I know these curvature components, then I can sort of, yeah, given the curvature components, it's kind of a closed system for all of the Ricci coefficients. Right? In principle. Okay. So now I move this over. All right, so that's the first stage, first set of equations. But of course, I need a way to understand the curvature components. And here there's something very interesting, and this is again an insight which goes back to Christodoulou and Kleinerman, which is sort of I mean, why it's kind of like in what sense are the the Einstein equations are supposed to be like wave equations, right? We know that if you pick some nice coordinates, some wave coordinates, they literally become quasi-linear wave equations. But I'm not working wave coordinates here. I'm working sort of this geometric way. So where is the sense that these equations are hyperbolic? I mean, certainly when I write them like this, I mean, there's no hyperbolicity. I mean, well, this is a very weird way because I have to know the curvature, and then I'm saying I can integrate this. There's nothing hyperbolic yet. Well, one place you can see the hyperbolicity is in what's very nice is if you combine the Ricci equals 0 condition along with the differentiated Bianchi equations. Right. So so you have these, so there are these Bianchi identities for curvature, right? So we have the differentiated Bianchi identities, right? So this says something like, right, if you take a covariant derivative of the curvature tensor and you sum over and you put the plus or minus depending on the sign of the permutation, and you do that sum, you get 0, right? It turns out that this is true, of course, this is something automatically true for any curvature tensor. So what's weird is this plus Ricci of G equals 0 ends up giving you well, you can think of it this way. If you freeze the Ricci coefficients, you will have basically a something that's like a first order hyperbolic system for the curvature tensor. And if you don't know what that means, it's fine because I'm going to tell you in a very something in a very pedantic way. All right, so it turns out, so by putting these together, we can write out a system. We can write out some set of equations. Actually, this is not how the way the hyperbolicity was that I'm going to understand it here is not sort of how Christodoulou and Kleinerman kind of used it in the stability Minkowski space. Then there they use something called the Bell-Robinson tensor, but something interesting. The way I'm going to explain it now is something which ends up being more flexible for lots of applications. All right, so you can write out these set of equations in terms of something called what people call Bianchi pairs, which is maybe a bit unfortunate because sometimes it's not, it's involves more than two things sometimes, but okay. You'll see why it's called a pair. So in schematically with this basically is the following. So again, so imagine now you have some curvature, let's call it capital psi1, and that's one of those curvature components that, right, this might be, it could be a tensor or a function, or we have rho. There's one was called rho, that was a function. There's the alpha AB, that was a two tensor. So whatever, one of those. And then, so these pairs, they'll come, and then you'll have, let's say, you might have psi2, so two of them. Then what does it mean that these constitute a Bianchi pair? It means that, you write out these equations, and then you simplify things using the Ricci condition, and maybe in derivatives of the Ricci condition. Then what you get, you can find the following. So you'll have the following structure. So you'll see something, and I'm just going to write at the principal symbol level. So I'm going to neglect the lower order terms. So you'll see, you can have some equation for the nabla 4, say, of psi1, right? This, right? You can write as, this will be equal to, at some point you'll see, I'll write this as, this is my notation, not standard, L slash. This will just denote some angular operator applied to psi2 plus things that are lower order, plus lower order terms, which include nonlinear terms. I mean, you can think that in reality, these lower order terms, again, there are different ways you can write them, and it's important to write them in different ways, depending when you're trying to prove different things. But schematically, you can imagine that everything lower order here will be a product of some curvature component and some Ricci coefficient. All right. So it's so if you freeze the Ricci coefficients, it's linear in the curvature. Right. I mean, this is sort of this thing, right? If you have like a nonlinear, like if you have f squared and you differentiate it, it's then linear in the derivative of that, right? That's all that's going on. Okay, so we have that'll be one part of the Bianchi pair. And then where's the hyperbolicity is that this thing will satisfy an equation of the following form. It will satisfy an equation, nabla 3. So on the right-hand side, oh, I keep missing these questions. You should, when you ask a question on Zoom, you should say something so I hear it at a reasonable time. But yeah, so the psi times psi, that does not mean that the two psi's are the same. They can be the same. Sometimes they're the same. Sometimes they're not. Right, so we'll have nabla 3 of this, and this one will equal minus L bar adjoint applied to psi1, again, plus lower order terms, which are of the same form as that. All right, so if you have some curvature component, and again, sometimes there's we'll see it later when I write out the actual formulas, or at least some parts of the actual formulas. There's a version of this that involves 3 of them. We still call it Bianchi pair. All right, but this is the basic idea. Well, I mean, you can sort of imagine that. I mean, if you have some tensorial object, you can write it in terms of scalar objects, then maybe it sort of seems to involve 3 things, but still really 2. Yeah. Okay, so if you have something like this, so why is it hyperbolic? Well, it's hyperbolic. Well, I mean, first you have to say, what is hyperbolic? Okay, we can have a very long digression talking about what hyperbolicity means, but I keep a very, I'm in favor of a very pedestrian viewpoint of what hyperbolic means. Hyperbolic means that I can do something like energy estimates for my system. Now you might ask what energy estimates are. Well, so let's see what they are. So what's the point? Why am I so excited that the equation looks like this? Oh, and then let me say what. So let's say L bar is some operator, sort of it's a geometric operator sort of on, just acting on, it's operator defined with respect to G slash, if it involves derivatives and involves covariant derivatives with respect to G slash. That's why I write it with a slash operator. And then this is the G slash adjoint. Right. So I have a volume form. Of course, I mean, I never said, in reality, I fix an orientation. I never said that, but that was implicit what I'm talking about. So I mean, I have some differential operator on acting on a sphere. I can, integration by parts gives me the definition of an adjoint. So again, just so that we're all on the same page here. So what does this mean? This means that, so I integrate on any given SUV. And again here, I mean, the way it's sort of, I'm being agnostic. I mean, we don't know what the tensor types of all these things are, so we don't know depending on what kind of tensors they are, there's some correct way to contract them together with the metric G slash, but whatever it is, you write that, this should equal the integral of SUV F against the adjoint. Okay. So yes, this is a first order differential operator. Does that make sense? What I'm saying? So for maybe it just like one example could be the divergence, right? So for example, if psi2 is a one form, then this might be the divergence. Just take a covariant derivative and trace. Then the adjoint, well, we'll discuss about this. Okay, so we have that. So when you have this structure, you're able to do energy estimates in the following way. And again, maybe you've never seen the word energy estimate, so I'll just tell you what there's an estimate that sort of implicitly you can do here. That's very important. So then the idea is what you can do is, so at this level of schematic presentation I'm neglecting tensorial structure. So let's forget about the fact these are tensors. So you should really think it's like d by dv, of psi1 equals this plus blah, 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 and say du of psi2. For now, let's just think of it like that, right? And now the point is, so I'm going to multiply this first thing by v and integrate on the spheres. So then what I can do is I can take, all right, so s uv dv by 1. So we're going to pretend that psi1, psi2 are scalars. And let's do this equals 1 and this equals 0, right? Just to be simple. Okay. So then what I can do is I can integrate on the sphere, take dv of psi1 times psi1, integrate with the volume form. All right. Remember, slash always means the thing defined with respect to the induced metric on the sphere. All right, so this is of course equal to, so this is 1/2 dv of, right, this, split that. All right, then, so I can pull that out. All right, up to, again, lower order terms, right? Of course, why are there lower order terms? Because of course the volume form, right, can change for each u and v, because g slash might be changing, right? So, but when the derivative hits the volume form, then I'll just see this, right? So in that sense, it's lower order. It'll just involve like integral of c1 squared. This is the derivative of something. That will not involve a dv derivative of this thing on this thing. Maybe I should just sort of. I mean, it'll be sort of controlled back. Okay, and then so this I can write like that, but on the other hand, this is equal to, integral of s uv, and then I get L bar of psi2 times psi1. plus lower order terms, right? Okay, now I can do the same thing here, right? And what do I get? Well, I can skip this intermediate stuff and go to the final stuff. So I'll also get, this is really hard with the word here. So I'll also get that du of SUV of psi 2 squared equals integral of SUV, and now I'll get minus L bar psi of psi 1 times psi 2 d volume plus stuff that I'm ignoring that involves less derivatives. Okay? This makes sense so far? Yeah. Shots of that. All right, and now let's anyone see what's the magical thing? Be bold.
Great.
So what's this? What's the key thing? What's important about the relation of these two things? I mean, this is the minus of this, right? So this is the thing. So the point is that I can add these two things together. Okay. All right. So the point is that these things, so integral SUV of, so this minus this equals 0, basically by definition of the adjoint, right? And so the point is, so therefore, the result of all of this is I derive something like this. Well, well, maybe it's fine. I'm not writing it's all the integrals are all respectively the induced volume. All right, this. So I have derivatives. So I have some integrals of the quantities I'm interested in controlling. These are going to be some curvature components squared, the integrals on the spheres. I take the derivatives of those expressions, and I take this particular combination. And then over here will be all sort of lower order terms. What does that mean? Meaning these are things which sort of involve either just the derivatives of the curvature component squared, or of some messing up my I hope nobody was confused by that. Right? These are all curvature, right? Oh my God. Like everywhere. All right, you see things which are, so you took the derivative of some quantity and you got something which now does not, is just back in the quantity. So now this is something that you can so now you can integrate this and you're basically you're able to estimate these L2 norms. You'll be able to, what you're going to do is then integrate. So you'll integrate with respect to, say, du dv. All right, and then apply the fundamental theorem of calculus. And what you'll do is you'll relate sort of the values of these functions at some later times. Of course, there's this u and v kind of geometry going on, right? So you might think it's something like, so if here's some, I don't know, some u equals, we'll get more comfortable with all of this later. This is the first pass of this ideas. This is some v equals this. So you can integrate, say, over some region like this, say in u and v, and the fundamental theorem calculus. So I mean, you can integrate up to say, so you integrate, say, V naught up to equals V1, and say U up to U1. And so what you'll get is, the all of the integrals of this expression you'll get this way. Because you're integrating in U and V, and you do the fundamental term calculus in V. So you get all these estimates here, and then in U, you'll get all the estimates here. And all of that will be controlled by sort of, just the integral over this rectangle of the same quantities. All right. And such an estimate, I guess maybe, if you're not familiar with hyperbolic equations, maybe it's hard to, maybe it's like, why, like, what the heck are you talking about? Why did we spend a whole lecture where that was the punchline? But this is the availability of such an estimate is sort of the hallmark of a system of equations being hyperbolic. And part of that has to do with what do I say it? I mean, wait, so what should I erase now? Now I erase this. Part of that has to do with so-called Gronwall's inequality, which maybe is worth just quickly. Quickly reviewing for you. So remember I guess there's something like that there. Gronwall's inequality, which what you should think is sort of the end result. Well, I'm going to write sort of a kind of a 1D version of it, but so the end result is something like, so if you have a function, right, of say, which depends on say time, and if you know that sort of, so yeah, so let's suppose tau is going up from 0 up to some t, and if you know that sort of for every tau in 0 to t, that f of tau is less than some a plus the integral from 0 to tau. Let's say there's some b out here of f of s like this. So say a and b are constants. All right, if you have something like this implies actually that. So what's the idea is that you look at this and it says, well, I mean, if I could differentiate this sort of, basically this is saying that f should sort of schematically think it's growing at most exponentially, right? And well, Gronwall's inequality is just some simple little ODE trick is that, yeah, that's true. So this does imply that f of tau is less a times exponential of v tau, right? And so basically, this is, so you can imagine, so this kind of structure, of course, there's a u and a v here, so maybe it's like they're like two directions, but basically this kind of estimate, so you're controlling these things at the v's and the u's in terms of the same quantities now integrated in u and v, because of this kind of structure tells you that at least, okay, of course, as tau goes to infinity is not very maybe such a great estimate, but at least for like small amounts of time, you can control like there's some you can say something about how it might sort of evolve. And that is again an extremely pedestrian take on what hyperbolicity is. So a set of PDs are hyperbolic if there's some way that the principal symbol allows for this kind of structure. Right. And then because of Gronwall's inequality, you're able to prove some kind of estimate. And these are the estimates that ultimately allow you to prove these local well-posedness statements that I asserted to you. All right, so questions about that? The same methods for other types of PDEs. Well, anything that's hyperbolic.
Hyperbolic.
Well, you'll say, yeah, sure, for parabolic equations also have, well, yeah, so that's fair. Then you could complain that, you have an energy estimate for a parabolic equation. But a parabolic, I guess, no, that's fair. But a parabolic equation is not a first order equation, let's say. Or it's not it has it's sort of, no one would think that the heat equation was a hyperbolic equation. So if you have sort of, so these if you have a first order system like this, then it's sort of the proper definition is something, you look at the principal symbol and it's something about the eigenvalues all being real and distinct. I mean, it's not, you can give various formal definitions, but yeah. Okay, so that's sort of first pass at the Bianchi equations. Again, we're going to see this, we'll see this more concretely. And I'm also going to do, well, I'm going to talk about the characteristic initial value problem. I'm going to state that theorem explicitly, and we're going to, well, at least I'll work out the analog for a nonlinear wave equation, and then we'll see these things. We'll see more concretely where all this nonsense means. For now, there's some more structure that I want to say about it, and then I want to write some more examples of the actual equations that show up. Right. So, okay. So I haven't told you at all. I've just been talking about what the principal symbol of the equations look like. Principal symbol meaning the terms, the highest number of derivatives. However, the other terms that show up are extremely important in general. You know, among other things, because they're nonlinear and they can make things blow up. Now, okay, of course, in this particular setting, they're just explicit formulas for everything. However, the formula they're pretty complicated. And it's useful, well, it's always useful, even if they weren't complicated, to have some heuristics or understand some structure behind what's going on. One of the useful structures that's been discovered here involves something called signature, which I'll explain now. Right, so there's something called signature. And roughly speaking, so you can look at the signature of a Ricci coefficient or the signature of a null curvature component. And what is the definition of this? Well, it's one of these schematic things. So basically you say the number of E3s that show up in the definition. So this is minus the number of E4s. Right, that looks a little silly, but but just let me just give an example and you'll see what I mean. So for example, the signature of chi hat is -1. So why? So this is just the trace-free part of chi. So chi, and this is the same as the signature of trace chi is also -1. So why is that? That's because chi is G of EA, E4, EB. So you look in the definition of it, it only involves, there's no E3 and there's an E4. So 0 minus 1, you get 1. Right. So that's what this definition means. Then for the curvature components, it's easier because the curvature components just have, it's literally, the null curvature components literally are defined as the curvature tensor with certain E4s and E3. So you just count and then you do this formula. All right. So then, all right. So you can, so for example, this one is -1, whatever. Continue. So so the Ricci coefficients will, so for Ricci coefficients, this will range, this will be -1, 0, or 1. Right? Okay, so there's that.
But I,
Yeah.
but I didn't see why it is well defined. Is it well?
Well, it's defined via this.
In the sense that this is invariant under different writing.
Well, I mean, the only thing, right, when you do the double null gauge, that guy always comes to like 30 minutes or something and then leaves. It's fine. But he keep coming. It seems so upsetting to me. Sorry. So anyway, keep in mind, so when you do the double null gauge, so everything, things are not tensorial with respect to, or at least not manifestly, with respect to changing E4, E3. E4 and that we made a choice. There are different ways we could pick different null hypersurfaces. We could change all of that. So where the formalism is geometric with respect to the sphere so far, right? And of course, I mean, not to say you can think about what happens if you change null frames, but you can try to understand that. That's not what we're doing right now. So E4 is a fixed thing. The only thing that's sort of ambiguous or is geometric, I mean, these things are.
Yeah.
But I mean, this definition doesn't involve those things. So it is, I mean, this is a tensorial object on the S2 that, I mean, you see what I mean? So it's actually not ambiguous. The other way is you can just take that as a definition.
Okay, okay. It
Um,
will be defined only for little c and big c.
yeah.
Okay.
Yeah.
Sorry. Zero quantities or zero quantities, which is fine.
No, this is a tensorial quantity.
Okay.
Um, yeah. I mean, it sort of looks like a silly definition, but I'll see it's useful in the following. Well, I'm going to tell you what it's useful in the following. All right, and then okay, so then sort of for curvature, just to make sure we understand the definition. So remember we had, for example, so alpha AB is Ricci of right, this is EA, E4, EB, E4, right? So that's two E4. So this one, so signature of alpha is -2, right? Because they're two E4s. All right, and in general, the signature of a null curvature component will be -2, -1, 0. Can have one more. Right. Then there's sort of some rules. So then you can also, if you well, you can think that it either follows from the definition, suitably interpret it, or you could take this as like a definition. If I take nobla 3 of a quantity, then that should be, the spirit of that definition is that should be 1 plus the signature of psi, right? And then the same for a curvature component. Right, and then same thing for nobla 4. It's the same. Okay, and then you can also, right, and then, well, again, it sort of follows the spirit of the definition is that if you do some angular operator, an angular differential operator, that should just be the same as, whatever, it should be the same, right? And then the final rule that we need is what happens for a nonlinear, say, nonlinear expression. And there, what we do is the rule is we should just add. So, for example, if you have psi1, contract it with psi2, well, I should say this could be or. This works the same. Or, I mean, any combination of Ricci coefficient or curvature one, what you do is you add them. So this will be S of psi1. S of psi2. Okay. So now, so all of these things. So now what I can do is, so everything that shows up in a null structure or a Bianchi equation, all the individual terms that show up in the equations, I can compute the signature of. And the claim, it sort of follows from how these things are derived geometrically. The point is that signature is conserved, right? So this is the big point is that, so null structure equations and Bianchi conserve signature. Well, this is sort of the informal way to say it. This means that each term that shows up has same signature. Right, and so this constrains the type of, so in a given, so even without computing the whole, even without, of course, we actually, here we do have all the formulas, and it's still useful. They're sufficiently complicated that it's still useful to, well, let's say if you go to higher dimensions, there's similar things that work, and then it's even more annoying to compute things. This constrains the type of nonlinear expressions that can show up, basically, because of this. And the reason this is true, why is this true? Well, it just has to do with, well, I guess I'll tell you some of the equations, but if you just think about how the things are derived, so all of the stuff starts with some, like I told you, you have a definition of the Ricci coefficient. It's just some, inner product of a covariant derivative of something else. And, then you apply a derivative, you commute something to make curvature, you convert covariant derivatives to the SUV derivatives. But I mean, all those processes will keep the fours and threes the same, basically, if you just think about it for 5 minutes. So it's like, this is a very useful observation. It's not a sort of a, once it occurs to you, it's like obvious that it's true in a way. And again, if you don't even like that obvious proof, you can just look at all the equations and see that it's true. But it turns out to be very useful. Moreover, I mean, So it constrains the terms, but and this is of course before you, especially if you don't have much experience with the hyperbolic equations at all. I mean, the somehow there's this thing that different, one of the things that makes the subject sort of harder or interesting is that, it's not when you're trying to understand various phenomena, it's absolutely not the case that all of the Ricci coefficients will satisfy the same estimate, or all the curvature components will satisfy the same interest. I mean, so the different ones are going to do different things, and you have to understand, particular nonlinear interactions between these different behaviors and what happens. And often, in many, many things that people have understood in the subject, the sort of, for example, you're studying a stability problem and you want to do a perturbation. You want to understand how various components of curvature fall off. They have certain powers of t, say as t goes to infinity. And ones that say involve more, they turn out to be like good directions and bad directions. And if they're more sort of good directions, more in the, those ones, it's natural to expect they have more decay, for example. And then you go and you have to understand, you're trying to prove that that's the case, and you go to look at some nonlinear term that you're worried about. This kind of structure might, like, without you looking at the formula, you can immediately know, well, because it sums up, and I know if basically I might be able to, my guess might be that the decay of these is related to signature already. And then this kind of structure allows you to easily see that everything's consistent without, needing to go to all the formulas, which of course, where you can also make a mistake easily. Right. That's just being very schematic. Okay, so that's important. And again, we will see we'll see that already when we discuss the characteristic initial value problem. The how, certain nonlinear terms, because not all directions are the same, certain nonlinear terms would make your theorem you're trying to prove not true. And signature considerations allow you to see, without needing to compute exactly what happens, allow you to see that everything's okay. All right, so that's sort of, like I said, this whole lecture today is all this a first superficial pass, just to like a preview of some of these things. All right, so in the last 12 minutes, first of all, are there any? All right, so I mean, I think I've delayed as long as I can without, now I should write some of these equations. I mean, there's probably not too much point in writing all of them. It'll also just take a while, and you can just, they're in many papers. But let me just write some, but okay, it's important to see some, so right, all this is a little too abstract. I mean, you need to understand more concretely what's going on. So I wrote here, so now I erase this. I'll start maybe with the most famous one, this Ricci-Drury equation, which we saw in spherical symmetry, right? All right, so the Ricci-Drury equation, which is the source of the incompleteness theorems and the singularity theorems. So this one, okay, so here's the first. So I'm going to write some of the null structure equations. Some of the. So by the way, if you want to see these written out, I mean, there are many, references. I mean, if you can Google, I mean, the many works in relativity in the last like 15 years, which use this gauge, and all of them at the beginning of the papers, the equations will be written. Some sort of textbook treatments. There's this book by Kleinerman and Niccolo, which is of course somehow, yeah, that was written at the sort of earlier days of things, and people maybe think about things a little differently than how it's written there, but that is something that parts of it are like a textbook. So if that's useful, this is a book by Christodoulou on formation of black holes. There's a long discussion of sort of null frame formalism. Even though he writes things slightly differently than how most people write them, then you can look at my papers about naked singularities, for example, will have the equations at the beginning, et cetera, but many, many different ones. Well, also later we'll talk about this result that Jonathan Luke, well-posedness of the characteristic initial value problem for the Einstein equations. You can look at his paper. It also has the equations. Anyway, so here's like I said, so just some of the null structure. So some of the null structure equations. So here's Ricci-Drury. So this is an equation. So I'm writing it first. It's actually not representative. And that it's not representative, and that this one does not. There's no curvature component on the other side of it. All right, so here's the equation. So now before of trace chi. So So by the schematic that I told you, everything I should see on the right-hand side should either be linear in the curvature or some nonlinear, a quadratic nonlinear expression in the Ricci coefficient. So then I also just told you there's no curvature. So I should just see quadratic expressions. And I do see that. So I see minus 1/2 trace chi-squared minus this expression. Right? So this is a tensor on the sphere, so I can take its norm using the spherical metric. And then there's, yeah, I say this is, oh, sorry.
Like just like derived by the same person, or is it related to the previous? Also fun.
Well, I don't actually know the exact history, but I mean, I guess presumably Reichituri used it in a way that became well known. Yeah, I mean, it's just these are equations for how the second fundamental form of a surface propagate in a null direction. And the point is that somehow, like secretly, there's a Ricci curvature. It's a particular thing that where what is really showing up here somewhere in here is like a Ricci E4 E4. So even when you do the singularity theorems, you have, and you'll have a sign. Like if you want to put some matter with the dominant energy condition, there's a sign here. And these equations are famous because somehow you're able to prove things by kind of just analyzing them without you can forget about all the other stuff. Yeah, because I mean, and the thing is, what's also because there's no curvature here that shows up. And because somehow the right curvature thing that shows up is Ricci, but if you're at vacuum, that's 0. So that's nice. And then what you see is that it's like a propagation equation for trace chi. These terms all involve trace chi, so you can sort of think of them really as part of the same equation. And then the only kind of term that makes it not self-contained is this term, but that term has a sign. And in the and that sign allows you to prove those without, so you can sort of be agnostic about exactly what's going on here, and you can still prove things. That's sort of why it's like a famous equation. Yeah, so it's unusual so that's sort of one of them. So in the case of the Einstein scalar field equation, there was an equation that involved, so remember, so in that case we have the area of the spheres is given by R, right? So the trace of the second fundamental form tells you how the area of your surface is deformed, right? In general in geometry, right? The trace, like a minimal surface is trace 0, right? Like your critical point of the area function. So this in spherical symmetry is related to the derivative of R. And we had that equation which involved 2 v derivatives of R. Then at some point there was a quadratic thing. There was a scalar field d phi dv squared. Like I said, that often the shear sort of corresponds to derivatives of the scalar field. This is one example how you can see that. So in spherical symmetry, there's no shear because everything's spherically symmetric. So everything chi is always a multiple of the metric. So in spherical symmetry, this is not here, but there's some matter, and then the matter serves the same role. Okay, so that's that. Another yeah, so some of the equations are like, so then you can also look at Nabla 4 of chi hat AB. This one sort of is in a way has less content. So this one looks like this. Right, like I said, you should see things quadratic, the Ricci coefficients, and then curvature. Oh, that's locked. It's weird. It's very secure. -2. Great, so that's so the other one. So yeah, that's just what it is. All right. So yeah, so you see sometimes when you write these equations, I might write, so why did I put this term here? So there's some ways of writing it where I might put this, well, the trace chi one's a little weirder. So one thing is I mean, one of the things you could always think about is what's going on like flat space, so on Minkowski space, where most of the things are 0, but not everything. So even on flat space, of course, the area of the sphere is R. And so, I mean, so trace the derivative of R is not drdv on Minkowski is not 0, right? It's whatever, again, 1 or 1/2 or 2, depending on whatever you're doing. Yeah, this thing is not 0. So that's why sometimes you write it sometimes you put, if there's sort of terms, so if you take in these null structure equations, you see a quadratic interaction that involves trace chi. I mean, you think like if you're sort of, it's good to think about what happens near Minkowski space. That term's sort of not zero, so you sort of think of it as this is not really a quadratic like term in some sense, because it's kind of, you can think of its Minkowski value, there's like a 2 over r plus some error. And so sometimes we write that on this side. But like this would be zero in Minkowski space, this would be zero. Anyway, so that's one example. Okay, so we have 4 more minutes. Okay, so there are other what do I want to write? Well, I'll write some more later, but okay, so then let's write right, so that's that one. Yeah, this one, like I said, this one, whatever. So just, and then you can also do novel 3 of chi hat. This one's sort of maybe a little more interesting. So this one you get, but you also, by the way, you can check the signature, right? So chi was a signature is -1. If I take novel 4 of it, it's -2. That's -1 because it has 1, 4, that's -1. So -1, -1, -2 works. This is also -1. Anyway, see, it all works. Magic. Here's so yeah, and so for example, just like one very silly thing where curvature, where signature sort of helps you. You might think, so these terms were these are the non-zero, the ones that are not zero on Minkowski space, like trace chi or trace chi bar. So you might want to know like which one shows up. So just by signature considerations, you already know that if if you're taking novel 4, then the only thing that can, if you have the same Ricci coefficient, the only thing that can multiply it in a novel 4 equation, it has to be trace chi, because trace chi bar is not consistent with signature. So that's already just an example of how there are things that you can deduce about the structure of the equations without computing just by signature considerations. And so similarly, when I do novel 3, I can only see a trace chi bar thing. And in reality, signature is also related to what number you get here. It's slightly more, it's not quite just from that, but it is also these numbers that appear here are also related to signature. That appear in like this linear term. Okay, let me write the other terms, and then we'll call it a day. So, and in fact, you often see these. Then there are these. There, in a lot of these equations, you apply your novel 4, novel 3 to your Ricci coefficient. There are various terms that are then linear back in the Ricci coefficient. Usually, there might be a trace chi or trace chi bar term. Which one shows up is related to this in signature, and the number is also actually related to signature. Similarly, you will often see some term with omega or omega bar. Again, for novel 4, you can only see omega. For novel 3, you can only see omega bar. That's signature. And it also turns out that the number here is also constrained by signature. All right. So signature, again, tells you a lot. All right. So you see that, and then you get some more interesting terms. So here's something. So this is one. You see something more interesting. -1/2 trace chi bar. All right, and so this is one of these kind of angular operators. So I was depicting all these kind of things with L slash. So this is an example of an operator, an L slash type operator. So what is this? This is like it's the symmetric trace-free gradient sort of. So in general, if you have some like a one form, then this operator is this -1/2, or no, is it -1/2? With the factor, yeah. Okay, so so if you trace this, because the trace of the two-dimensional thing will give you 2, right? So if I take the trace on these two indices, I get something 0. So this is but it's symmetrous. Right? And this is the yeah, well anyway, anyway, that's just the operator. It's in a suitable L2 space, this sort of is the adjoint of the divergence operator as acting on trace-free symmetric tensors. So yeah. It looks just like the Dirac equations of interaction. Yeah, I guess could be. All right. So, okay, it's 5:01. So I'll end here. So I'll write, like I said, there's not much point in me writing all these equations. I mean, we just, obviously if you're going to work in the area, it's something you need to get more familiar with them. At the level of this course, it's not that important. Just trying to give a bit of a flavor of them. Talk about this structure thing. I'll write out some of the Bianchi equations later. And then what I'm going to do is I'm going to, and I'll talk about, I have to talk about also how you do, how you commute these equations with derivatives to do higher order estimates. So I'll do that, and then we'll switch gears and we'll start talking about the character. I'll state you the theorem, which is the well-posedness for this system for characteristic initial value problem. And then after stating that, I'll switch gears again and we'll sort of study that problem for a wave equation because we need to develop some intuition about this. And hopefully that won't be the whole class, but yeah, anyway, so we'll see where that takes us. And then once we have those technical tools at our disposal, we'll be able to return to address the original goal of trying to understand these self-similar things for the vacuum equations. But these are all tools that we need to do that. Okay, okay, so I'll end there.